Now, for our next topic, which would be the research and design on bamboo as an alternative material for housing. Our next speaker is a graduate of Bachelor of Science in Civil Engineering at the Colombian National University and a graduate and took his Master's of Science in Civil Engineering at the Los Andes University. A structural engineer from Colombia who dedicated his entire career to research and development of bamboo building systems. He's one of the authors of the Colombian Bamboo Structural Design Code and collaborated actively in the development of the Peruvian and Ecuadorian Bamboo Code as well. Currently, he is part of the ISO committee for timber and bamboo structures representing Colombia, and he also is the director of the committee of the Colombian Bamboo Code Update. Since 2014, has been working with the Base Bahay Foundation, a Philippine-based organization using the cement bamboo frame technology to build social low-cost houses. Ladies and gentlemen, please welcome our next speaker, Engineer Luis Lopez.
Hello, everyone, and thank you for the welcome, and thank you for having me today here. It's an honor and a pleasure to participate this year in the ASEP 28th convention, international convention. So today I will, let me share the screen, sorry. Second. Okay. Hope you can see the screen. So my presentation today is about bamboo construction. So one thing about bamboo construction is that it's not something that is completely strange for the Philippine culture. So bamboo is part of the Philippine traditions and is part of the history of this country, but unfortunately, it has never been treated as a structural material like other materials, conventional materials like concrete or steel. Has been always treated as a second-hand material of the first mass timber. So today I want to show you many possibilities of this material and how a material like bamboo can help the developing of the country and help also the industry to improve. So let's talk first, what is bamboo? So bamboo is a giant grass. It belongs to the Gramineae family, so it means it's related with the corn and that kind of, and the grass that grow in your garden. And there is some estimation that's not clear. Some researchers say that there is 1,300 species around the world. Others say it's 1,600 species around the world. As you can see, most of the species are located in the tropics and in semi-tropical areas, so in America, in Africa, and in Asia. So Philippines, of course, is in the middle of the area of the bamboo. But bamboo is a very successful plant, so already colonized Europe and other parts of the US and territories that before don't used to have bamboo. So it's a very efficient plant. So there are some differences between wood and bamboo. So first, bamboo is not a tree. So it's a grass. It's a grass, a giant grass that has a cane, but it's not a tree. As you can see now in these two cross sections, there is evident differences between both materials. So first, the wood of the trees has two types of growing processes. They grow longitudinal and grow radial. The bamboo only grows radial. So you cannot estimate the age of a bamboo based on its diameter. You can do that with the wood, with timber, but not with bamboo. Bamboo grow when the sprouts or the new shoots emerge from the ground already has the final diameter. So you cannot identify the age of the bamboo based on the diameter. Other characteristics of wood and bamboo is that the most strong part of the wood is always in the center is called the hardwood. So it's the strongest part, and the weakest part is a more clear part here in the periphery of the tree. In bamboo is completely the opposite. So the most strong part is the periphery, and the weak part is the center or the inner part. And of course, there is always empty space. It's a hollow cylinder in the middle. And maybe one of the biggest difference is the speed of growing. So timber wood grow very slowly. So if you plant trees, you need to wait maybe 20 years to harvest or to cut the trees. Aside bamboo that you can see growing. So bamboo grow at a rate of 10 centimeters per day, more or less. So you can have a mature pole with the structural capacity just after 3 years. So there is many history about the use of bamboo in the humanity. So this, for example, some pieces that was found in Argentina and belongs to a community that used them 8,600 years before Christ. So it's a proof that bamboo has been always stay with the communities, not only in America, also here in Asia. Why is so important? Why we should pay more attention to the use of this kind of materials? I think in our profession, we are always looking for the high tech advance, and that's fine. It's perfect. We need that. I mean, we cannot build infrastructure with bamboo. Definitely, we cannot build a high rise with bamboo. That's clear for me, and I think for all of us. But there is many kind of constructions that can use bamboo, and we are not using that. So we are affecting indirectly or directly our environment. So remember that construction industry in general is responsible of around 40% of the greenhouse emissions in the world. So that's a lot. And if we just refer to the cement and concrete industry, we are talking about 8-10% of the carbon and greenhouse emissions came for only from that industry. So that means everything that we make as structural engineers are putting some kind of emissions in the planet. So we need to fight against that. So with using how we can fight against that. So bamboo can be a very, very good weapon against the climate change. So how is that? Okay, bamboo is a natural product that during its life can sequestrate carbon. And when you use bamboo or even wood, that carbon stored in the bamboo or in the wood will be stored during the lifespan of the construction. So you are keeping that carbon out of the cycle of the normal cycle of the gases. So, for example, this is a very simple drawing. I mean, the process is definitely much more complex than this one, but we create carbon because the cars, the industries, many things, and all that carbon goes to the atmosphere. So after that, the plants, including bamboo, sequestrate that carbon and transform in timber and wood. In this case, in the canes. If we don't touch those bamboos, after a while, maybe 10 years, 12, the bamboo will die in normal cycle of life, and it will be rotten, and the carbon will return to the atmosphere. So the cycle of bamboo sequestrating and liberating carbon is only 12 years. But if we take few of those poles and we convert in a house or components of constructions, and that the lifespan of that house is 50 years, 40 years, or even more, we are broken that cycle because all that carbon will be stored in that construction for more time than in the nature. But that is why using natural products or natural-based products you can fight the climate change. So we need to use more of this kind of product in our industry. It's not that we become fundamentalists of the climate change and everything should be done with bamboo, but we can change some components of a construction for bamboo and create a big impact. That's why I prepared this example. I want to show you, you will be surprised with these numbers. So I apologize, maybe you will find some Spanish words, but because this was made in Spanish, I have to convert. But what I want to show here is the comparison of a steel purlin versus a bamboo purlin. So imagine that you have a warehouse, a metallic warehouse, of everything is metallic, but you decide only change the purlins. Instead of using steel purlins, you use bamboo purlins. And the rest of the construction continue being a steel construction. You just use a sustainable material in the purlin. So it's a secondary element, no primary element of the structure. So I look for two sections that are structurally compatible or equal in all the characteristics. So I found this C profile, very thin laminated I think it's cold rolled profiles here. So it's 10 centimeters high and 5 centimeters side. And I chose a bamboo, quite big, 13 centimeters diameter and 11 millimeters wall thickness. So if you compare the section, of course, is the one is in C, the other is a cylinder. But let's start to see the properties. So the modulus of elasticity of this steel is around 200 gigapascals. But the bamboo is only 17.4 megapascals. So we are saying that the steel is around 11 times more than the bamboo. The moment of inertia in the steel is only 66.6 centimeters for potence, and the bamboo is 772. So the steel is less than 0.1 of the bamboo. So you can see that the lack in modulus of elasticity is compensated with a very big diameter that is provided by the nature, by the way, by the inertia. So the relation between modulus of elasticity and inertia for the steel is 135, and for the bamboo is 136. That means, structurally talking, the two sections are equivalent and resist the same. So the density for other side is 7,800 kilograms per square cubic meter in the steel, and only 10% of that is bamboo, 710 average for bamboo. So now I want to go to the end of this table. So let's check here, material carbon embedded. So for steel, we are talking that the kilograms of carbon per kilogram of material is around 2 kilograms, and for bamboo is 0.2. And now I convert that to the equivalent of a 3 meters per limb. So for a 3 meters per limb, per linear meter, I will have 6.45 kilograms of carbon emissions, of course. And for bamboo, I will have 0.87. So the difference, that's per meter. So the difference is actually quite high right now. We're talking about that to produce a steel purlin, it'll generate around 7.4 times more carbon to the atmosphere. And this carbon produced by the steel is, of course, all the process of the extraction of the mineral in the rock, the process in the steel industry, and after that, the process in the industry that make the profiles, and even the transportation to the construction site. And here in the bamboo, we are talking about probably some kind of tool that was used during the harvesting of the bamboo and the transporting and the treatment process. So you can see that the difference is quite big. But let's see what happened here in this graphic. So we have for the 3 meters beam, we have almost 20 kilograms of carbon emissions, and for a 3 meters bamboo beam, only 2.6 kilograms of emissions. But the thing here is that the bamboo also has some carbon that was sequestrated during his life and is inside. So it's a negative carbon. It's around 10 kilos it's around 3.5 kilos per meter. So when I make the subtraction of the sequestrated carbon and the bamboo and the carbon that was emission, so the remaining balance is actually negative 7 kilos. So when I use perlin that is made in bamboo, actually I am not generating emissions to the atmosphere. I actually sequestrating those emissions. So the difference is huge when you compare. It's almost 30 times, but even it's not only 30 times you are saving carbon, you are storing carbon. So that is why we need to start to use more of these materials in industry. So today I want to show that sample just to put in context, because you will start to see this kind of comparison more and more in our countries like Colombia. Colombia is a tropical country like Philippines, so in the tropics here we are very lucky because there's a many things of everything. The tropics are abundant in everything, so we don't care too much about climate change. But Philippines now is facing a lot of problems with many typhoons passing, and we will feel the climate change coming and making more disasters. So we need to start to work in these things. So there, I want to continue now talking about bamboo structure. So there is many kind of bamboo structures actually, and there is many systems of construction with bamboo. So here, for example, I'm showing you only one of those systems. This is like a spaced structure, like three-dimensional trusses that can make with bamboo. So you can do like pavilions, even this is a church in Colombia. All these constructions are made in Colombia. And it's a kind of a style of construction that is very common in Latin America and even in Bali for bamboo. But there is more systems. And of course, tradition is important, but we are not talking today about traditions and Baha'i cubos. I want to show this picture just to remind all of you that how important bamboo is in the tradition of the Philippines. But the problem of this traditional kind of construction is that there is no durability at all. So that is one of the reasons when you say to the people that you want to build with bamboo, they have a lot of concerns, because we have this kind of constructions also in Colombia. We call it chozas, you call it here Baha'i cubos, and it's a kind of transitory construction, beautiful. It's very beautiful, but with a lot of problems in terms of structure. And it's a kind of construction, of course, is not designed for any structural engineer or even an architect. So we need to improve this. We are not changing the tradition. The tradition can coexist with the advance in the engineering, but we need to use well a material that is here and can be used properly as a structural material. So these are more or less the kind of construction systems that you can find with bamboo. So first we have the three-dimensional trusses or special space bamboo construction. So here, all the bamboos are responsible to resist lateral and vertical loads. So it means I need bracing, I need a lateral system of resistance normally composed by diagonals made of bamboo or steel. So there is another system that I will show in bit later. It's called, we call it here in the Philippines, cement bamboo frame technology. It's a shear wall system when we use light frames of shear wall light frames of bamboo. And it's a shear wall system. So it's different to the first one, of course. So this is the skeleton of the house, and this is how the house looks at the end. So we cannot see actually any bamboo, but it's a house made of bamboo. And there is other systems like this one. Is the innovation of a Filipino. The company is called Cubo. You have some media notorious in the last 2 years. And this is laminated bamboo. So you take the bamboo, you pass the bamboo to a process, and you make like wood, like plywood, and rectangular sections of solid bamboo elements. So that is probably the future of the industry, but the costs are quite high but it's very interesting. You can make very nice designs like this one. And this last design, this is in Mexico, is a lamination without glue. So this structure is made with bamboo slats and connected with some kind of screws and bolts, and you can make all these structures also. So these are the four most common designs that you can systems that you can use using bamboo. So here some samples also of what is happening with bamboo in the Philippines. So bamboo is getting a lot of attention, especially for architects and few engineers also. So we have this industry, Kubo, that is making laminated bamboo. So they are starting to do some houses that are completely, these walls are solid bamboo. We have another firm of architects, Shanghai Architects, that they made this beautiful structure in Calatagan, and this is the Polo Club in Calatagan, and that was made for the ASEAN Games, if I am not wrong. So you can see how the bamboo can also apport to the aesthetics and the economy of these regions. This is Hawaiian Collective, enterprise, a social enterprise in Dumaguete, working also for roofing constructions and proposing new editions of the Baha'i Kubos. And this is MS Studio Co. From Cebu. They inspired in the Balinese construction style, and they made this kind of beautiful cabin in Cebu. So as you can see, bamboo is getting a lot of attention for designers and architects, but we are always behind all of this advance. When I say the engineers, the same situation happened in my country 20 years ago. We have a group of architects proposing beautiful structures, but the engineers don't know how to analyze. We don't have a resistance for the material. We don't understand the connections. So we have to wait until we make a lot of tests and we can understand the system. So understanding the standard world for bamboo is just in their early stages, to be honest. Maybe 30 years ago, 20 years ago, there was not a single standard for bamboo in the world. So the first standard in the world appears around 2000. It was a local code in California for characterization of structural bamboo, more like a grading standard for bamboo. And after that, many countries has been implemented their own national standards. So that's for you to understand. For example, Colombia was the first country to introduce bamboo in their national building code, followed by Peru and Ecuador. Right now, Brazil and Mexico are making their own standards. So maybe by this year, Mexico will approve their standard. India, since 2009, has a standard for vernacular bamboo construction. China has plenty of standards for laminated bamboo, engineered bamboo, but not for round poles bamboo. And the ISO, where the office is in Switzerland, had two bamboo standards since 2004. So right now we are working with ASEP and the HPRDI in Los Baños, Laguna, and together with Base Baha'i to explore the possibility to create a bamboo standard for the Philippines based in the new ISO standard for structural design. I will show you a little more about that. So this is a small chronology of the bamboo standardization in the world. So it started in 2000 with the standard from ECBO. It's a standard based in California. It's for acceptance criteria for structural bamboo. So that was like the first known standard, but this is a standard that is not for obligatory use or is not a national code. So in 2002, Colombia created the first standard for Bajareque construction, that is the shear wall system with bamboo. And that was created during an earthquake that destroyed one of the regions in Colombia. So at that time, Colombia became the first country with a bamboo standard in the world. In 2004, ISO published the ISO 22156 for structural design and the ISO 22157 for mechanical properties test. And in 2009, Colombia made its second structural bamboo standard for three-dimensional trusses, and India made his standard also the same year for vernacular construction. 2010, Peru published their national building code, following by Ecuador in 2015. By 2018, ISO published a new standard for bamboo grading, and this year the ISO has approved the new version for bamboo structural design code. And this is very important because this new standard can be, the ISO 22156 can be the basis not only for the Philippines, for many countries that wants to implement and establish their national building codes. By 2022, we expect the new Colombian standard and the Philippine standard. Why not? So basically, the two most important standards that exist in the world are these two. One is the NSR10, this is a Colombian national standard. This standard has been working for, or the creation of this standard has 20 years of research and development in the country. And it's very complete, and actually is the basis for the Peruvian and the Ecuadorian. And also a lot of the contents in the NSR10, the Colombian Building Code, this is the equivalent of the NASEP for Colombia. So many of these contents are included in the new ISO 22156 that will be published in June. So it was approved in the last meeting of the ISO Committee for Timber and Bamboo, and it will be published. And what is the content of this standard? Well, it's exactly like a timber standard. So you can find visual grading, you can find allow stresses and modulus of elasticity, all the coefficient modificators for temperature, humidity, duration load, working group. You can find all the formulas to design elements in the axial load. You can find the formulas for bending, for shear parallel, connections, everything. So you can design an entire structure with this standard. No, you can design a column, a beam, you can design a truss, you can design a structure completely, and understanding also the way that you have to do the modelation of this kind of structures. So we hope with this committee led by Professor Alessandro Garciano from De La Salle and other participants from the PRDI and Los Baños and our team in base, we can make the Philippine version of this ISO standard soon and propose to ASEP and authorities to use this material in the building code. So there is many standards types like materials, construction products, even there is a standards of process already, like treatment and all. So now I want to show you a little bit about the tier one system or Bareque technology that we call it, how we call it in Colombia, because it's what I am doing here in the Philippines, and we already has been built more than 1,000 homes in the country for poor people or people with financial problems. So we are supporting victims of typhoons, also people living in risk areas with this kind of construction. So first of all, I want to tell you what is Bareque. Bareque is just the name of the technology. This is a very beautiful town in Colombia, in the coffee region. And all these colorful houses that you see in the picture are bamboo houses. It's hard to believe, but these bamboo houses has more than 100 years old already. So for those that were bad in geography, Colombia is located here in the north part of South America. And as you can see, it's actually almost in the same position as Philippines in terms of the position in the globe, no? So we have the same weather. So that is why we have bamboo. That's why we have almost the same temperature. That's why we have beautiful women here and there. So it's the same. That's why we fight in Miss Universe. So it's a bad joke. So the thing here is that in this region, many towns were built using this system because it was quite hard to access to that place. And during the time of the colonial time, during the time during Colombia was under the Spanish Empire, so many people used to build using this system. So we cannot confuse the Bareque with this kind of structures. So this is a three-dimensional truss of a space structure where the bamboo is the only structural material and all the resistance is supported by the columns, the diagonals, and the connections. So bamboo here walls is different, but also has its roots in an European system called wattle and dab. So you can see this house. I was in UK 2-3 years ago, and I visited the house where William Shakespeare grew up. And this is a house from the 17th century. And we're talking about a house. This house has no bamboo at all, of course. You can see, but the system is similar to the origins of the Bareque system in Latin America. So this is a timber structure, but all the walls are made with this kind of system that use branches of wood and mud and things like that. And also here in the Philippines, you have that. During the Spanish time, there was a construction system called Tabique Pampango, of course from Pampanga, but also very common use in Siquijor in the area of Dumaguete. And with this system, you can see here this picture is very similar to what you see in the Shakespeare House in UK. So it's an European system. Here they, instead of using wood branches, they use bamboo strips or bamboo slats and mud probably and other things. So it was more related for religious construction like churches or convents, things like that. And unfortunately, it was not very popularized, but still you can find some of these constructions. So means the cement bamboo frame technology that we use here in the Philippines also has its roots here. It's not something imposed by a Colombian engineer or something like that. Is connected because we made part of the same empire, we can say. I mean, Colombia and Philippines both were part of the Spanish Empire in certain time of the history. So this is how the system evolved in Colombia. So again, you can see here the bamboo slats and the bamboo studs in the wall. So in the beginning, the wall was filled with soil, as you can see here, and this is the kind of architecture. So you can see there is not too many difference between this Tabique Pampango and this old house from the 19th century in Colombia. So today you can find these houses 200 years old still. And the secret of the durability is, of course, a good selection of the material during the time of construction. The farmers who built these houses 200 years ago select very well the material, but also the bamboo is never exposed to the environment. So that helps a lot the durability because bamboo has a very bad behavior against UV radiation and rain and humidity at all. So if bamboo is covered, like here in these walls, so the house can last for many years. So this system evolved in the coffee region of Colombia and reached its climax around the 20s of the last century. And you can see this kind of palace made of bamboo in the city of Manizales. And once they have access to cement, they use cement to improve the system. So they were able to make this kind of facades. And they were able even to make 3-4 stories buildings. So you can see this building under demolition in 2005. It's a 3-story building, and you can see all the bamboo stuff that was also in the city of Manizales. But unfortunately, when these conventional materials arrive and the concrete industry push a lot, the system started to be not used too much or relegated to rural areas and poor people. But it was relegated to this use. So this is a typical bamboo house in the rural area of the coffee region in Colombia. So actually, I grew up in a house like this because I came from the province in the coffee region in Colombia, and this is the new architecture that people is doing with bamboo there in the rural areas. But in 1999, there was a very strong earthquake in this region. The earthquake kills around 2,000 people. And you can see in the pictures that all these bamboo houses survive very well. So you can see here in this size, these are 2 bamboo houses, but the concrete houses and the masonry constructions suffer a lot. Actually, it's calculated that 98% of the victims came from masonry and concrete structures. And 2% for other kind of structures, including bamboo constructions, but that's nothing when you compare with the others. So here also you can see the old bareke houses there in the back in perfect condition, and here all the destruction of the earthquake. This is the Brazilian neighborhood that's completely destroyed. It was a neighborhood made of a simple masonry and no structure at all. So that's just for like cards. And here, this picture is very interesting. We don't say that this kind of bamboo constructions are indestructible. No, they also collapse. But as you can see here, look the way these walls collapse. So this is a house that collapsed, and the wall, it seems to try to keep its integrity. It's hard to disassemble. So when you are doing the collapse of a masonry house, like a CHB or brick house, you will have a rain of bricks under your head. But here, it's like the whole wall. This was a two-story house, and this is the whole wall of the second story that falls completely. So it creates a lot of space that can help the people to survive. So this is the owner, actually, the picture. This is the owner of this house. He survived, and even his dog. And then the house, of course, was completely destroyed, but he were able to survive. Aside, the weight of these houses is 2 to 3 times less per square meter, talking of masonry houses. So there's more possibilities to survive if you get hit by an earthquake in these houses. So doing that, the Colombian government decided to make a research about mechanical properties, because we are talking in the 2000s, the year 2000, and we don't know what was the resistance of bamboo. We don't know the modulus of elasticity. We're talking 20 years ago. So 20 years ago, the engineers of the world don't know what is the modulus of elasticity of, or what was the modulus of elasticity of any bamboo species. There was few research around the world, almost nothing. If you research for papers, you find no more than 5. Some theses, and that's it. So we have to research about the mechanical properties. This is, of course, a Colombian bamboo species, wagwa, that was introduced in the Philippines also like 15 years ago. So there's some plantations of this material. And you can see the characteristic value of this species is around 24 megapascals. So we are saying that characteristic value of bamboo is almost the same of normal concrete. We're making concretes of 21 megapascals, 25, 26 megapascals. So it's a material with very good structural capacities, competent at all. So for tension parallel is even better, but the problem is that the connection will fail first. Bending 26 is still very good. Modulus of elasticity now is much better. We are doing better tests that we can measure better the modulus of elasticity. So, for example, for Hawaiian technique, we are getting results of 17 gigapascals or 17,000 megapascals. And shear parallel is very similar to wood. So this is a very fast test of bending. So this is in Los Andes University and the Laboratory of Structures in Bogota. So you can see, first, the flexibility of the material is amazing. So it's a material with a very long elastic range sector, and so we can have a big deformation in the elastic part of the stresses, and then and before you have the failure. So it's a very flexible material. It works very well during the earthquakes because of that. So at that time in 2000, in the year 2000, this was my bachelor thesis, by the way. So I made around 75 tests of different configurations of shear wall of bamboo, or the Vareke system, of cement bamboo frame system. So here's some results. So we have, for example, the system number 2 have a resistance between 24 kilonewtons per meter to 32. We have this system 1, that's the green, with the pouring capacity, because these legs that has the system in the bottom and it was resisting between 12 to 14 kilonewtons per linear meter. And these big format walls, even with a window, resist something between 18 to 22 kilonewtons per meter. In general, we are talking about an average resistance of 21 or 20 kilonewtons per meter. That is not bad for a very light system, especially if you see this wall here is made only with nails. So it's a very, very, very simple structure. So after that, we made some tests of three-dimensional models using the same walls. And the idea was to check if we can predict the result of these models. If we can predict means the system can be normalized and can be included in the building code. Because one of the problems with all these vernacular systems is that the results are always very random. So you can have very strong specimens and other very weak. So it's hard to normalize. But that's not the case with Bareke or cement bamboo frame. So we have very consistent results, and we were able to predict the behavior of these models. This was a monotonic test, by the way, not a check table test. So this is a reaction wall, and we apply loads in all the directions, but using just a monotonic load. But later on, in 2012, we were able to use for the first time, the first shake table in Colombia was set up by Los Andes University, and the first specimen that was used in that shake table was a two-story bamboo house. So you can see here the process of construction. They are installing the panels, all made in bamboo. This is a small shake table. I think it's 4 meters by 4 meters, if I'm not wrong. And here's a short video about that test. We applied a cover earthquake to this two-story house. And that was in 2012, the test. And okay, so as you can see, there is not many damages in the house, only few cracks, and that's all. So the house resists very well. Actually, in the laboratory, they applied the earthquake 7 different times to see what happened, and they have some damages in the plastering, but the houses keep all its integrity and was never close to collapse. So it showed that system is very good in terms of earthquake resistant. One of the reasons is first is very light, so the mass is 2-3 times less than a concrete house. Second, is more flexible, so move easily, and the elastic portion of the bamboo is too high, so the brief will recover almost totally after the earthquake. And the other reason is that the relation between the force that has to resist versus the resistance of the system is very efficient. So the system was very good. So in 2002, as I mentioned before, Colombia introduced that system in the National Building Code. For that time was National Structural, Seismo Resistant 98 Colombian code, and Colombia became the first country in the world to have a building code for BAM. So I will, well, the time is running and I still have a lot of things to show, but I want to show you this experiment because this was a great opportunity I had in my life in 2008. Very famous Colombian architect hired me to make the structural analysis of one of his bamboo building structures, but also to lead a full-scale test. So this is the specimen for the full-scale test. This was the model, was made in SAP 2000 nonlinear to check this test. So you can see, sorry, the dimensions of this structure you can compare with the size of the car and the people here. So this is a 25 meters span and 15 meters high. Only the walls has 8.5 meters. So what is this about? This is a project called the Nomadic Museum. It's a temporary exhibition that travels all around the world. And the architect of this exhibition is the Colombian architect Simon Velez, but the artist who presents his work is a Canadian photographer called Gregory Colbert. So this is the exhibition inside, and this is funded by Rolex Foundation. And they built this. This is the building in Mexico City, in the Zócalo, in the center of the Mexico City. And it's a free exhibition, so stay there, the structure for maybe 3 months, no more than that. And people go to visit to see these pictures, and all the building is made in bamboo. So this was the Mexico project. I was not participating in the Mexico project at all, but I was hired for the Brazilian project. So the Brazilian design was a little different. The roof in the Brazilian project was planning to have a live grass. The span was big compared with the Mexican one, and the configuration in the floor plan also was different. So they do it that due to the Brazilian code doesn't have bamboo, the authorities of Brazil request a full-scale test to be sure if they allow to build this in Sao Paulo. Because only in Mexico they have 6 million of visitors of the exhibition. So they want to be sure in Sao Paulo, that is also a huge city, that the people is safe at all. So they request this test. So you can see this is the specimen with the alive grass. You can see the grass here, and the walls was made in bamboo covered with these metallic plates and with some flat bars here to work like connectors between the bamboos and reduce the slenderness of the bamboos. You can see the human scale. Actually, this is me during the day of the test. So you can see how big the walls were. So, and the test that we made, it was very simple. We load this structure with 16 tons of sand, but instead to put the sand in the roof, because it's very dangerous, we just put a lot of cords coming from the roof, and we put all the sand in these bags of 40 kilos. So we divide the weight in 5 tranches, and we apply around 3.2 tons in each tranche. So, and we measure the deflection. Of course, this is my witness. So I see every 3 tons, if the deflection of the structure is the same, means I am in the elastic part of the spectrum, and not in the elastic that if it's in the elastic, I have to stop. Just to tell you an anecdote, when we arrived, this was made with the Brazilian authorities, sent by the government, and also the people from Rolex Foundation. So initially, in Brazil, there is no earthquakes, by the way. So they never request a lateral load test. Even they don't have typhoons, nothing like that. So they only request a vertical load test. But when they arrive, they request a lateral load test. So we say, no, we don't prepare that, so let's do it the vertical test, and we will see how we solve that in the coming days. And we applied the first 3 tons, and we went to sleep because it was too dark already. We will planning to continue the test the day after, and that night there was an earthquake in that region. I know it's hard to believe, but there was an earthquake around 5.5 magnitude. The epicenter was located only 20 kilometers away of the place. It was deep, 120 kilometers deep, something like that. But it was really strong because the epicenter was very near. So actually, it was so scary during the night. It was 4:30 a.m. So I take my car. I went to the site of the test before everyone's arrived. So I just want to be sure that the building was there, no? Because we will resume tests at 8. So at least I have time to escape. No, the truth was the building was perfect. And when the Brazilians arrived, they say that they never felt an earthquake in their life. So this building can resist that earthquake. It passed the lateral force test. So it was one case in a million, I think, the probability to have a real test with a real earthquake during a test. So I think just few people can tell that story. Anyway, this is important because these tests help us to understand the behavior of this kind of structures that are completely different to the barrique structure. So these are this is the deformation of the top of the roof during the application of the vertical load. So you can see here the date and the load. So first load, we applied 3 tons and there was a 1 centimeter deformation. We went to sleep the day after the earthquake, we have like half centimeter deformation without adding load. And after that, we add another 3 tons and the deformation increase. And you can see that every 3 tons we add, the behavior is quite elastic. No, it's the slope of the line is always the same. So it means we are always in the elastic part of the spectrum. So we continue until this point. This is the 6 tons, and we leave the building loaded for 24 hours. And 24 hours later, we measure again using topographic equipment, of course, and we have more deformation. And here we cut the cords. And you can see this was the recovery after 24 hours. The building recovered all of this. And 2 days later, it recovers even more. At the end of the whole process, we have a residual deformation. That means the building was shorter by 1.5 centimeters. And now this purple line you see in the bottom, it was my prediction using the SAT 2000 only there. So it was really, really wrong. I mean, very, very far away from reality. So my prediction was 2 centimeters global deformation, and the reality was around 6 centimeters. I'm not taking into account the 24 hours load of the structure. So it was a difference of 4 centimeters in the numbers provided me by the software and the reality. So I have to understand what was happening, why. So the explanation, it took a while, but once you understand, it's very simple. The problem were the connections, of course. So many of these connections are made by hand. This is probably the most common connection in bamboo, fish mouth connection. So this is almost a handicraft. So you see, there is a space. It's impossible to make a connection that is completely, closed. So there is millimeters or fractions of millimeters of space here that when you load the structures, those gaps have the tendency to close. And of course, you can modulate that in software. You use springs and things like that. But at that moment, we were not thinking in that. So we were just understanding what was happening. So, and of course, one single connection is not, you cannot perceive any deformation maybe. But if you have a structure of this size and you have maybe 2,000 connections, so the fractions of millimeters that are closing all together convert at the end in centimeters. So how you can compensate that? Well, I make the most simple way. Of course, you can complicate your life at the point as you want, making sprints and all of that. But I just reduce the modulus of elasticity of the materials to 0.33%, and that will affect the global rigidity of the structure. And this is the adjusted line. So with that, we start to understand the concepts to make models with this material. And all those concepts are incorporated later in the National Building Code of Colombia and transfer also those concepts to the ISO standard. So without those concepts, so actually more than concepts are advices for the engineer how to modulate these structures in a software and the things that need to have in account. You will ask, what is this hole here? This is to inject mortar or grout, because this connection cannot resist anything if it's not full with something that has at least the same density of bamboo, because if not, this internet will collapse when you have a tension load here. So these are the normal components of a fish mouth connection. So very simple technology, by the way. This is not rocket science. You can see here a 3D and how to make this connection. So probably people say, oh, bamboo could be very complex. Yes, but if you start to analyze, it's very simple. This is a fish mouth with a J bolt. This is another fish mouth with another J bolt, and that's that. And you have some flat bars to connect all of that transfer loads from one element to another. So finally, I think I have 5 minutes more. This is about Best Bahay, our foundation. So we are doing socialized house using bamboo here in the Philippines. The reason we choose, or the reason why Hilti Foundation chose Philippines to make this project is, of course, Philippines has around 25% of the people living under the line of poverty, probably more now with the COVID situation. And aside of that, we are in the middle of the typhoon highway, 20 typhoons per year, earthquakes every year, flooded. I mean, you have all the natural disaster that exists in the world. I think the only one you don't have is snow, but the rest is here. So Philippines is a very vulnerable country with a lot of challenges, but also a lot of opportunities for innovation. So in 2012, I came the first time to the Philippines together with Corina Salzer, the engineer from Hilti Foundation, and together we made a lot of tests in APRDI to understand the properties of the Philippine species. So here we made some tests of walls also. We did some tests in wind. So we built these 3 houses in Bicol. We installed a weather station and wait for a typhoon. In 2013, we built the houses. In 2014, Typhoon Glenda, this yellow line here, and these are the houses, actually hit the houses. The eye of Glenda passed just a few kilometers beside the houses. And these are the houses after Glenda. So 2 important things in the picture. First, the weather station collapsed during Glenda, and the highest speed that was reported was 185 kilometers per hour at this point, but other weather stations report 220 kilometers around this area. And the only damage of all these 3 houses was this small roof, part of the roof that nothing is not related at all with the bamboo construction. It's just that there was a missing test screw or something, but not it's because the fault of the bamboo. And of course, traditional Bahay cubos cannot resist because there is no connections, strong connections, there is no foundation, there is no bracing. So, and then the cement bamboo frame at least have some kind of mortar, so provide weight also to help the structure to stay in the ground. So this is a very short video about one of our projects in the Sorsogon that was hit by Typhoon Tisoy. Okay, so what you see in the video is the houses survived without any damage, and the families were very happy. And the houses were also in the point of impact when the typhoon make landfill. So the cement bamboo frame technology is a technology that is very good for housing, for 1-2-story houses. So for low density construction, use local materials, it's typhoon resistant, earthquake resistant, fire resistant. So the firewall that is double cladded can resist even 2 hours, protecting the fire or keeping the fire from one side to another. That is what is required in the law. And insect resistant because the bamboos are very well treated and last forever. The technology is accredited by ITEC. And these are some model houses that we are building. So all of these are bamboo houses, but the bamboo is hiding in the walls. You only can see it inside the house, but not outside the house. So with that change in the way that you locate the bamboo or put the bamboos in the walls, you can make these houses last forever, like the Colombian houses that has 200 years old. So I can say that the lifespan of this house is equivalent to a conventional house like CHP or concrete house. So aside of that, of our social housing project, by the way, we have completed already 1,000 homes in the whole country. So 1,000 families that now live in one of our bamboo houses. But aside of that, Base Bahay, together with Hilti Foundation, decided to set the Base Innovation Center here in Manila. So in Makati, we have a laboratory when we can do different kind of tests. So we have this universal testing machine when we can do mechanical properties tests and connection tests. We have an area where we can train people in how to use the technology, how to fabricate the walls and things like that. And we are setting our reaction frame. So actually the reaction frame is in place. What we're waiting now is only the arrival of our dynamic actuator that we already built, but will arrive maybe by next month or July. So by the end of this year, we will have a reaction frame fully operational where we are going to test shear walls. So, and we are signing agreements with many universities around the world. So right now, locally, our main partner is De La Salle University, but we have also agreements with PUP, with UP, and with University of Santo Tomas. Those are our local partners. International, we are working with Coventry University from UK, with ETH from Zurich, with the Hong Kong Science and Technology University, with Universidad del Valle from Colombia, Pittsburgh University from Europe, US, and even with the company ARUP. Yes, ARUP has a bamboo division. It's hard to believe, but they have the bamboo division, and it's not in Colombia or in China, it's in London. So in their headquarters in London, there is a group of engineers that are in charge of natural materials, and bamboo is one of their materials. So we are working very close with them, looking different topics for research. So the idea is to have a cooperation between these international universities and the local universities and bring all the knowledge from abroad to the Philippines and convert Manila in the hub for bamboo research in the world. So these are some images of our research right now in the laboratories. This is a research between Coventry University and the La Salle University in our laboratory when we are testing composite beams made of plywood and bamboo, tad or platinum bamboo. So it's a composite material. So we are taking advantage of the shear resistance of the plywood and combining with the good modulus of elasticity of bamboo. So we are trying to create a new material that can replace wood, for example, that is very expensive in the Philippines. Okay, so with in Dumaguete, we're working with Kawayan Collective and Foundation University and also Coventry doing the implementation of the ISO 19624 bamboo grading. So we are understanding the anatomy of the Philippine bamboos there. And only with De La Salle, we have already done research about the shear resistance of 5 bamboo species of the Philippines, and also we are testing 5 different species in bending. So that's all. Too many things that I want to show, but the time is over. So I think I finish on time. So thank you very much.
Thank you, Engineer Luis Felipe Lopez, for sharing us your knowledge about the bamboo as an alternative material for housing. Now we'll go on with our question and answer. I will be reading the first question. One question goes, in the context of comparing bamboo to steel, with the relatively low elastic modulus of bamboo, it requires more quantity as compared to steel in order to achieve the desired flexural rigidity.
It depends. As I showed in the sample of the two purlins, the lack in modulus or elasticity of the bamboo is compensated with the inertia, because the section of the bamboo is the most efficient inertia section in the world. When you have the centroided and the mass far away from the centroided, you have more inertia. So when I make the comparison between the C profile and the bamboo, all the lack or the missing part in the modulus elasticity was compensated by the inertia. So when you make the EI modulus, or the modulus of rigidity, is the same for both. So the answer is no.
Okay.
But you can compensate.
Okay, thank you. Now we'll go on with our last question. How do you preserve the bamboo for longevity?
Yeah, this is very important. Nothing of all the things I show you can be possible if you don't have treated bamboo. So that's is one of the points that you need to be very strict. So we in base we establish 5 treatment facilities all around the country. So we have one here in Batangas, we have in Bukidnon, in Davao, we have in Murcia, in Negros Occidental, in Dumaguete. So without that, you cannot produce quality materials. So bamboo need to be treated using some chemicals. So some people use borax and boric acid. We use another chemical that is called perimetrin that is very effective. So if you make the process of treatment very, very well, you will have no problem with these insects, neither with bok neither with an eye. So you can be sure your bamboo will last. So I just tell you some numbers. When we arrived here in the Philippines in 2014 to make houses, the treatment methods was not really developed in the country. So we start to buy our bamboos for third parties, and we have a very high rate of bok infestation. Like 10% of the poles we bought were infested. So we need to do retreatments. It was costly, also hard to explain the people that process. So we decide to invest in research. We create our own method. We now treat with that method. And once we start to use our treatment method, we pass from 10% to 0.01% of inflation rate. So, but definitely, always when you work with timber wood, there is the possibility to have an infection. But in our case, it's very rare that we have that.
Okay, thank you. Now, we'll go on with presenting the Certificate of Appreciation to Engineer Luis Felipe Lopez. Reading the certificate, Association of Structural Engineers of the Philippines hereby presents this Certificate of Appreciation to Engineer Luis Felipe Lopez, as keynote speaker during the AIC 2021 20th ASEP International Convention. Signed, Maricon C. Pineda, Secretariat, Bonito Diconanan as GP, and President Ronaldo Asiso. Again, thank you, Engineer Felipe Lopez, Luis Felipe Lopez.
Thank you very much, Cecilia.
Thank you to our speakers for their enthusiastic presentation of their researches. We hope to see more of both robots and bamboo in the industry. And with that, our keynote session has come to a close.
All right, thank you so much, Meg. And now we are approaching the last leg of this convention.
For our last leg of the convention, we will be having the ASEP session. Let us welcome our session